Folks, this is why you came. This is the section that turns the magic of fuel economy into the science of fuel efficiency. Science has a way of converting one form of energy to another mathematically. For example, it takes 2,544.4 BTU British thermal units to make 1 horsepower. That's what the science charts say. But in the real world, in an engine, you're not going to get a full horsepower by burning 25,044 BTUs of gasoline. It's called thermal losses. Faraday's second law of thermodynamics says you're never going to get out of it what you put into it. Again, going back to the Mustang scenario, the 1970 boss maybe got 10 miles per gallon. It's kind of hard to tell because there's not reliable numbers. But meanwhile, the 2023 or 2021 Mustang is getting combined highway city 25 miles per gallon. So we look at the efficiency increase from the 1970 to the 2021, and the 5-liter GT, modern day, with the Coyote engine, puts out 460 horsepower. Compare that to the Boss 302 putting out 290. If you get the Mach 1 version, it actually has 480 horsepower. It's getting 1.5 times the fuel economy. It's 1.65 times the performance. Oh, and then there's emissions. We haven't even got to that yet. So the EPA says our engines are about 20% efficient. Is that good? We take a look at the old-fashioned brushed DC motor, been around for 150, 200 years. A good one's about 80% efficient. And not so good ones are less, but a good one's maybe 80% efficient. If you look at the brushless DC motor, these guys can go over 95% efficiency. And we compare that to a 20% efficient engine. Why is that considered good? So we take a look at how the conversions take place. The US EPA also says that if you take that same gasoline engine that's 20% efficient on gasoline and you run it on propane, now you're 44% efficient. That means that the B2 energy in the propane, the engine is able to get 44% of that out and actually convert it to power at the flywheel versus the 20% on gasoline. But if you go with natural gas, now you are 60% efficient. Same engine, just different fuels. Gasoline is a liquid. In order to extract the energy from the chemical gasoline, it first has to vaporize. Well, natural gas and propane are already in vaporous form. So we're going to lose out on some of those endothermic losses. So gasoline is also bigger. Pentane is a C5H12 molecule. Dodecane's a C12H26. But, I mean, look, CNG, LPG, C4 is natural gas. C3H8 is propane. They're much smaller. Now, it's kind of like the difference between trying to burn a log and trying to burn sawdust. An electric motor has 2 conversions, electricity to magnetism. The magnetism pulls and creates kinetic motion. So even the lousy brushed DC motor is upwards of 80% efficient because there's only 2 conversions. But a gasoline engine has to, first of all, vaporize any of the liquid fuel. And if you're saying, no, I got fuel injection, I get atomized fuel. Well, atomized fuel is just little tiny droplets of liquid. So you're still putting liquid into that engine, and that liquid has to vaporize before it can do anything else. And then we have to ionize that fuel. We have to take that big chain and we have to start peeling the hydrogens away, splitting the carbons. We also have to start splitting the oxygens in the air that we draw in. Now, once we have loose hydrogens, carbons, and loose oxygens, now we can combine the two, make carbon dioxide, water vapor, and we get heat out of the process. Well, engines don't run on heat. You don't believe me? Take a propane torch to the side of a lawnmower engine. You'll melt a hole in it, but it won't start running. So there has to be an additional conversion. That heat has to act on the air in the engine to create pressure. Now with the pressure, that pushes down on the piston, and now we get kinetic motion. So one of the reasons that electric motors are so much more efficient than the gasoline engine is there's very few conversions in comparison. Also, let's take a look at hexane. Hexane is considered one of the lightest elements in gasoline year-round. C6H14 vaporizes at 156 degrees Fahrenheit, 69 Celsius, and it takes less than 1 millisecond to actually burn. Burning meaning oxidize. But then we take a look at the other end of the spectrum. So in the summertime, you'll see upwards of dodecane. Vaporizes at 420 degrees Fahrenheit, which is, I didn't change the 69. But it takes over 33 milliseconds to burn. Now, in this frame, time-wise, we have the lights taking less than a millisecond, and the heavies can take over 33 milliseconds to oxidize. Keep those numbers in mind because now we have a parameter, we have a window on the fuel. Combustion starts out, and if you follow the bouncing ball there, you get a spark. That spark is going to attack the oxygen and the fuel molecules that are trapped between the electrodes, and it'll start ionizing them. And then as it ionizes them, it starts peeling the hydrogens away from the carbon and splitting the oxygens apart, and then they start reattaching with each other, forming water vapor, initially carbon monoxide, then carbon dioxide, and release heat. But it takes that spark. You have to put energy in to get it out. If you have an open container of gasoline, does it just automatically start oxidizing? No. But if you throw a match on it, now it'll start burning. It took the energy of that match to start that oxidation process. So you got to put energy in first. I think what I wanted to show on this slide is the blue curve. You initiate spark, and getting back to the previous slide, there's a flame propagation where you ignite only the fuel that's between the electrodes with a conventional ignition system, and then that fuel will start oxidizing, releasing heat. But that heat doesn't start contributing to power. That heat contributes to vaporizing more fuel and splitting apart more fuel and oxygen molecules, which then recombine and make more heat. And that heat then still doesn't power the vehicle. It vaporizes more fuel, and it starts stripping more hydrogens and carbons and oxygens apart, which then recombine and make more heat. And eventually, your fuel is about as vaporized as it's going to get, and you've pretty much broken down all the molecules, and they're recombining, so now your heat is contributing to creating pressure in the cylinder and pushing down on the piston. And it's all grayscale gradiated, where you have little tiny micro pockets throughout the cylinder that are at different stages of that process. And that's what that blue curve represents. You build pressure, and then as the piston moves down the bore, you're able to absorb that pressure into kinetic energy. So at 2400 RPMs, we're going to start with some simple math. Again, this, if you get it, the whole rest of the course makes perfect sense because everything fits in. You have a framework. If you don't get this, if you can at least get the gist of it, what I'm trying to say. So let's take an engine at 2400 RPMs. Now this is highway cruise speed. 2400 revolutions per minute, you divide that by 60 seconds, and that's 40 revolutions per second. If you do the math to see how much time is involved, 1 over 40 is about 25 milliseconds, 0.025 seconds. One stroke is half a revolution, so 25 milliseconds divided by 2 is 12.5 milliseconds. Now remember our window on the gasoline? Less than a millisecond to over 33 milliseconds. Now we know that our power stroke is going to give us, at 2400 RPMs, 12.5 milliseconds. Are we starting to see how things are starting to fit together? Now, at 30 degrees before top dead center ignition timing, that's about 2 milliseconds. So from the time the spark plug fires to bottom dead center, we might have 14.5 milliseconds. But wait, about a millisecond and a half, 22 degrees before bottom dead center, the exhaust valve opens. And it just starts bleeding off all that pressure. You may have gobs of pressure in that cylinder that's capable of doing work, but the exhaust valve just opened. It's just dumping it out. It's still burning. Don't believe me? Touch an exhaust manifold. No, don't do this. Please don't touch an exhaust manifold. I'm kidding. But you know that it's very, very hot. And the reason it's hot is because there's this blowtorch of still burning fuel going out the exhaust. So in reality, we have maybe 10 milliseconds at most to harness our energy. Gasoline burns, textbook, look it up in any encyclopedia, 41.5 centimeters per second. Now, looking at the frame, you'll notice that there's a little tiny 3 next to the cm, centimeters cubed. That means that it will go in 3-dimensional space at 41.5 centimeters per second. So the first stage is we're going to have energy that vaporizes the fuel, and then we now have free-floating molecules instead of clusters. So the liquid fuel would be a cluster. We vaporize it. Now we have free-floating molecules. Then we fracture them. Spark plug or the thermal energy from flame propagation. We're going to start breaking the bigger molecules into smaller ones, and the smaller ones we're going to start peeling individual atoms from. And we're going to split the oxygens. And this is all endothermic. So we have to put energy in order to start the process where we get more than that back out. So endothermic is we're putting energy in, and then exothermic is getting more than that back out, the actual burning of the fuel. And the oxygen is going to combine with hydrogen and initially produce what's called an OH radical, and then it will stabilize into water, H2O. The carbon will combine with the oxygen and initially create carbon monoxide, CO, and then will stabilize into carbon dioxide, CO2. When you look at how much of the total energy from the fuel is derived from the creation of water vapor, 65%. So 65% of the energy that is harnessed is because the hydrogens from the fuel combine with oxygen make water. 30% of the total energy comes from combining carbons with a single oxygen producing carbon monoxide. From the carbon monoxide to the carbon dioxide stage, that's your last 5%. So an abbreviated formula is we got a hydrocarbon fuel, we're going to add oxygen to the mix plus energy. And then we're going to get back out of it water vapor, carbon dioxide, and more energy. When we're looking at the total time frame, again, we said maybe 10 milliseconds from the time the spark plug fires to the exhaust valve opens. If you have a wrench on a bolt, all right, here's the bolt, and you have the wrench, and you put it here, and you just pull towards you. You're not going to move it this way or that way. You're just pulling it towards you, and no work gets done. When the piston's at top dead center, pressure isn't creating any useful work. But once the crankshaft rocks over and starts working its way down, now it's like we can start getting leverage on that wrench. We can start harnessing any kind of pressures and convert them to energy at the flywheel. And in physics, if you have that wrench at the 90-degree angle, that's where you're going to get the most leverage. It's kind of the same way in an engine, almost.